Hello, my name is Ben Albrecht. I'm a software engineer on the Chapel team at Cray, a Hewlett-Packard enterprise company. In this talk, I'm going to present about Arkouda, a project that enables Terascale data science at interactive rates for Python programmers. I'd like to acknowledge that Arkouda development is led by Mike Merrill and Bill Roos with the support of the Chapel team at Cray HPE, which is led by my technical lead, Brad Chamberlain. So to set the stage, imagine you are leading a team of Python programmers to solve an HPC scale problem, and you have the necessary resources available to you. How would you leverage your Python programmers to tackle that problem? Well, this is the problem space that Arkouda is targeting. As a teaser, I will show a couple of slides that I'll explain later more in detail. First, Arkouda's design. Arkouda consists of two components, a server and a client. The client interface is a Python module that lets a user connect to the server, create Arkouda arrays, and perform operations on them in a similar fashion as you would in NumPy. The server is a distributed Chapel program that interprets and dispatches operations from the client side, such as A plus B or sort some array. The arrays are distributed across the resources, and the operations from the client side are performed in parallel on the server, ultimately giving the Python programmer access to high-performance computing through a NumPy-like interface. And here is a teaser for the punchline of this presentation. These are some timing results for various data science operations using real data. I'll go more into this slide later, but the takeaway is Arkouda enables Python programmers to work with Terascale datasets such as 50 billion record arrays. It supports data science operations such as I/O, filters, and transforms. It provides a familiar interface through NumPy and Pandas-like API, and it completes these operations at interactive rates within the human thought loop. Here you can see these Terascale data science operations finish on the order of seconds. When a data scientist is working with a data set to extract some knowledge or information, they are going to perform a number of operations on that data set in no particular order. Things like sorting, histogramming, scalar reductions, and so on. In order for the data scientist to work effectively, the time between wanting to execute one of these operations and having it complete needs to be pretty small. In other words, they need to have an interactive session. This means that the operations cannot require things like recompiling the code, rereading datasets into memory from disk, or writing some amount of boilerplate code every time they need to try out a new idea. Most importantly, these operations need to run to completion within the human thought loop so that the data scientist does not lose their train of thought while they're exploring the data set. For the most part, interactive Python running in a Jupyter notebook on a large server fulfills these criteria for today, at least for data sets on the order of 10 to 100 gigabytes, which I would consider small to medium. It's worth exploring why Python can do so well in this small to medium range today. Python has a reputation for being slow, and it is true that it's pretty slow. But when a data scientist uses Python, they're not really using Python itself. If they're using a standard data science package like SciPy, Pandas, or scikit-learn, they're actually using the NumPy objects, NumPy arrays, and NumPy computational primitives under the hood. NumPy brings together a bunch of low-level code for things like linear algebra codes, codes written in C or Fortran, or a GPU language, and it bundles those up in Python objects so that data science packages that are built on top of them can expose them through a Python syntax. But under the hood, they're also calling C or Fortran. And this is very effective as it gets quite good performance on single node. Data science also demands scaling, though. So when a data scientist is exploring a data set, it is imperative that they use the entire data set in their exploratory operations. It is possible to take a sample of their data set. However, it is quite difficult in practice. For starters, getting an unbiased sample of their large data set is an incredibly difficult problem. And if they have a small measure of bias in their data set, that is going to skew their results significantly. Even if they are able to get an unbiased sample from their data set, there are going to be some higher order effects that they may not detect in the small sample. For example, if you imagine that you're measuring, you're counting all of the nodes in a graph with 4 or more edges, you're going to lose a lot of data points when you take a sample of your graph. And so data sets have over time outgrown the typical computer or server. A larger server today can hold in memory up to on the order of a terabyte, while many data sets easily exceed 10 terabytes. And so it's important for a solution for these data scientists to scale. Enter Arkouda. Arkouda tries to accomplish these needs of data scientists and serve ultimately as an HPC shell for data science. And it achieves this through 3 main components. First, it has a Chapel backend, which acts as a server to both store the distributed memory arrays and perform the operations on them. Secondly, it has a Python front-end client, which is intended to be used in a Jupyter notebook in an interactive session. And third, that interface has a NumPy-like API to give the users familiarity and a common framework for interfacing between Python and the backend libraries. So if you recall from the earlier slide where I showed NumPy serving as the gateway between backend performant libraries and higher level Python APIs, Arkouda is trying to achieve something similar, except instead of NumPy being for single node, Arkouda is trying to implement this bridge in the world of HPC and using Chapel as a crucial part of that gateway. So Arkouda aims to interface parallel distributed runtimes, languages, and libraries in the high-performance computing to higher level codes such as scalable data frames, feature extraction strategies, and large hypergraph libraries. So before I continue, I'll say a little bit more about the language Arkouda was written in, Chapel. Chapel is a modern parallel programming language. It's portable and scalable, running on anything from laptops to supercomputers. It's open source and collaborative, developed on the GitHub platform out in the public. And the goals of Chapel are to support general parallel programming and to make parallel programming at scale far more productive. And this is accomplished through making parallelism and locality first-class citizens in the language. When asked the question, why develop Arkouda in Chapel, it'd be hard for me to give an unbiased answer as I'm a developer on the Chapel team. But when asking the lead Arkouda developers, this is the answer we got. Chapel is a high-level language with C-comparable performance, both in terms of single node and distributed performance when comparing to C plus MPI. Arkouda developers chose Chapel because Chapel has parallelism as a first-class citizen. This makes it much easier to express the algorithms, the parallel and distributed algorithms that are necessary to implement a lot of these operations in Arkouda. Chapel is portable. It runs from a laptop up to a supercomputer, both portable in terms of performance as well as requiring no code changes to scale up to these systems. And Chapel integrates with numerical libraries, both single node and distributed. This owes to Chapel's native C interoperability, as well as many of these libraries are already wrapped and have an interface in Chapel's standard library, such as FFTW, BLAS, and LAPACK. Perhaps most importantly, the Arkouda developers chose Chapel because it's very close to Pythonic for a statically typed language, that is. And this is important because it lowers the barrier for users to modify the backend implementation if they need to. Say they want to modify how an Arkouda implementation works, or if they want to add a new feature to Arkouda, they can pull back the curtains and look at the code, and it's not that bad to work with for a Python programmer as compared to, say, C or Fortran or some other more performant format languages that Python would typically call out to. Just to demonstrate this, here's a quick chapel program. In this program, we create a 1,000 by 1,000 block distributed domain D, and then declare a distributed array over this domain. Then we loop over the domain indices in parallel and assign each element of the distributed array to a value. This program can be run on a laptop as one node or up to a 512 node Cray XC with no code changes required. Okay, so as mentioned before, the Arkouda design consists of a Python 3 client and a chapel server, which is hosted on the user's platform. It can be any arbitrary hardware, anything from a laptop to clusters to a supercomputer. And so the Python 3 user will be importing Arkouda as they would any Python module, and then they will connect to the chapel server that they've launched separately. Then any operations they do, such as creating an Arkouda array, operating on it, or destroying it, will be communicated via a ZMQ socket over to the chapel server. And on the chapel server, that message will be dispatched to the correct core module and the correct array in the distributed object store. Just to give you a clearer picture of this, here's a simple example where a user is adding two Arkouda arrays A and B and assigning that to an array C. So on the client side, this will create a binary operation between ID1 and ID2, which are the chapel's server side's representation for A and B. So the client will send that message over to the server via a ZMQ socket, and on the server, that message will be interpreted and then dispatched into the correct module, this case being the arithmetic module, and then there will be an argument lookup in the distributed object store to find the ID1 and ID2 arrays, which are A and B, and also it will allocate a new distributed array, ID3, for the left-hand side assignment. On the chapel's server side, we'll be doing a parallel execution to add those two arrays, and then there will be a return message that ID3 has been created so that the client side knows to store ID3 as the representation for C. So as a simple walkthrough of how a user would approach Arkouda, there's two steps for startup. The first step is to initialize your server in the terminal. So you run, if you've pip installed Arkouda, for example, you will have Arkouda server available to you. So you would run Arkouda server -nl is the number of nodes. So in this case, we're launching the server on 96 nodes, and that will spit out a hostname and port. You'll use that hostname and port on the Python 3 Jupyter client to connect to that Arkouda server. So here we've imported the Arkouda array, the Arkouda module, and we've connected to it with the hostname and port. As a toy workflow here, this example shows us creating a 2 billion element arrays consisting of random integers 0 to 10, and then multiplying those billion element arrays to form a new array, C. These arrays are then histogrammed with 20 bins. And that histogram, we are able, both the resulting array and the histogram, we're able to do some queries on it. And you'll notice here in cell 10, we are doing some NumPy operations, some NumPy calls, as well as some matplotlib calls. And that's by design for Arkouda to interoperate cleanly with existing NumPy infrastructure. So you see here our hist object, we actually have the ability to convert that to a 2ND array as long as the user knows that's going to fit onto their client hardware. Okay, and this slide shows some data science operations available on Arkouda, along with some timings that were collected for two 50 billion element arrays of 32-bit values. The timings were measured on real data that the Arkouda team was exploring in their actual work. And they just happened to be measuring the timings as they were working and exploring this data. And these timings were collected on a Cray XE40 over 96 nodes. So if we work our way down this table, you can first see that reading in an array stored as an HDF5 file type takes about a minute. We have some descriptive statistics operations such as scalar reduction, histograms, vector operations. These all took under a second to compute. Next, we have logical indexing. So logical indexing is getting all the corresponding elements of an array A, where array B takes a certain value. And this can be useful for analyzing tabular data. And that took anywhere from 1 to 10 seconds to compute. Moving along, we have set memberships, which took a second. Gathers are interesting. So gathers are highly dependent on the distribution of the data. So if you have a large number of repeated values in your array, you can get these network hotspots that will generate a lot of communication. So those can take up to 2 minutes or as few as just a few seconds, depending on your data distribution. And then towards the bottom here, we have some of the key operations that are most important to the Arkouda users. So that would be sorting. Sorting is key to creating sparse matrices, things like finding unique values, extracting features, and many more key kernels. And so sorting here takes 15 seconds, and it's important to know that 15 seconds is not dependent on the distribution of the data. If you're familiar with your algorithms, that's because this is implemented with a distributed radix sort, which has the nice benefit that it's pretty easy to implement a distributed radix sort, and it's going to scale the same regardless of your data distribution. We also have group bias, which took about 30 seconds, and aggregate by key per key, which took about 10 seconds. Now we want to take a look at some Arkouda performance numbers and seeing how they stack up against NumPy. Now the performance numbers in this deck or in this slide are normalized to NumPy. So that means that a value of 1 means it's on par with NumPy, and then greater than 1 means it's better than NumPy. And I've highlighted the values that are better than NumPy in blue and worse than NumPy in red, just to make that easier to visualize. It's worth pointing out right off the bat that serial Arkouda is more or less on par with serial NumPy. Which is pretty impressive because these Arkouda implementations are just a few highly maintainable chapel implementations written by a couple of Arkouda developers in a few months, and they are already performing at par with NumPy implementations written in C and Fortran that have been hand-tuned over the course of years. Moving along to parallel implementations, as we allow the implementations to utilize some of Chapel's parallel constructs, we can see that at 36 cores, we are getting some nice results, already up to 16x on some of the benchmarks here. And then as we move out to 512 nodes, what we're really interested in tackling with Arkouda, we see that we can get up to near 2000x for things like argsort, which is one of the most important benchmarks here, and up to 4000x for reduces. Taking that data and plotting it out as a scalability graph, this shows that we get some really nice scalability numbers. for a handful of these benchmarks. And the most important one here, again, is the argsort, which, as you remember, is implemented as a distributed radix sort. And just to try to materialize this into a concrete example, here's a sample result. So sorting an 8 terabyte array of IPv4 addresses using 18,000 cores can take just over a minute with Arkouda, which is pretty impressive. And this scaling is not limited to high-performance networks such as Aries. These graphs show Aries versus InfiniBand, and you can see that InfiniBand is performing on par with Aries across the board for these 4 benchmarks here. So a common question that comes up when presenting on Arkouda is what about technology X, where X could be a runtime library or language? For example, Dask is a common one that comes up. So I'll address that one specifically in this presentation. So in our experience, Arkouda significantly outperforms Dask. We've done a small benchmark comparing reading in an HDF5 file and doing a scalar reduction. For the size of 4 gigabytes per locale, Arkouda completes the entire process within under a minute. Doing the same process for Dask, even for a scaled down data set of 500 megabytes per locale, reading in the file takes 4 minutes, computing a sum takes 5 minutes, 5.5 minutes, and then the entire remainder of the process takes over hours before we just kill the process because it doesn't look like it's going to complete anytime soon. Now that said, we are not Dask experts. No one on the Chapel team is Dask experts. No one on the Arkouda team is Dask experts. So we can't say we've been doing anything correctly. This is using a pre-installed version on Cori. So we are looking for Dask experts out in the wild to work with to do a fair comparison. And this applies to other technologies as well. If you are working on a competing technology, or either up and coming or more established, we are happy to work with you to ensure a fair comparison to that technology. Dask configuration on HPC systems is not trivial. It typically takes some expertise to make sure you're getting the performance out of your system, from what we understand. Meanwhile, Arkouda performance out of the box is easy to get. Dask is not designed for shuffle-based workflows such as sorting, grouping, because it depends on things like lazy evaluation. Arkouda, on the other hand, targets these workflows specifically and scales without lazy evaluation. Having said all of that, to Dask's benefits, they are much more established and more featureful. They have better integration with Pandas and more supported data formats beyond HDF5 and excellent cluster management tooling. So the status of Arkouda is we're now well over 12,000 lines of Chapel code developed all within a year. The Arkouda developer said without Chapel, we could not have gotten this far this fast. And I think that's a testament to how nice it is to work with Chapel, how productive of a language it is. The project is open source. It's being developed on GitHub, and it's available on PyPI. I'll post links to that at the end of the talk. And it's being used daily and on a weekly basis on real data and problems by the Arkouda developers and users. As a quick summary, Arkouda is a powerful tool in Vision. It aims for NumPy pandas on terabyte scale arrays in seconds to minutes. It's a workbench for interactive HPC scale data science. Arkouda takes a unique approach to interactivity in HPC. Most approaches start with interactivity and try to build out to performance, whereas Arkouda is starting from performance and building out towards interactivity with this NumPy-like interface. And the next steps involved expanding the API to support things like actual data frames, sparse linear algebra libraries, and wrapping existing HPC libraries. And we'd also like to support multi-user sessions such as data sharing and access control. And that's all I have for this presentation. Thank you for listening. On this slide, I'll leave some links to some other resources, and notably Bill Roos's talk, who I borrowed some slides from this talk. You can click that link there to see his recent keynote as part of CHUBE 2020. Thank you for listening.